Okay, so this is our fourth topic in our last section, which means that actually after this one we only have a few lessons left. If I can give some advice, topics 4 and 5 kind of go together. What we're going to do in 4 and 5 is talk about how to integrate things that are a little bit more challenging. So topic 1 was really just an introduction to what integration is, which hopefully you're now aware of two things. First one is that when you integrate, you're really just reverse engineering a derivative, so you're going backwards. So if your derivative is, say you have a function f of x, and you find its derivative, that going this way right here is a derivative. But just like everything we've learned in math, there's an opposite operation, right? So adding has subtracting, multiplying, dividing. Logarithms and exponents are kind of opposites of each other. Sine and inverse sine. Well, when it comes to derivatives, the going backwards method of this is known as integrating. And for the most part, you when you do integration, you just kind of G-R-A-T-I-O-N. Not very good with my pen today. When you do integration, you more or less just look at it and say, well, hey, this is what it's going to be. And that works for a lot of things, but I mean, obviously there's going to be some more challenging things. And that's what we're going to work on in this lesson and the next one, is we're going to learn how to integrate using some special methods. And this is, there are probably at least 3 or 4 or 5 different kind of special methods of integration. There's integration by parts, there's integration by substitution. There are some other ones that I've learned in the past and that you might get to as well, all of which are little tricks that you can use to help you integrate things that are kind of challenging. Like, for example, this one right here, we're actually not going to integrate this one right here, but I'm going to use this to help illustrate how to use substitution. On this one right here, if you want to use the chain rule to differentiate, I guess let's hop into the example now. If I want to find y prime, this really is going to be x squared plus 1. And then the square root was a 1/2, so it's going to drop it down to the minus 1/2, which means you should really pull a 1/2 in front, right? The 1/2 comes in front, baby stays inside, and then when you multiply, you have to chain on the derivative, which is 2x. And I've previously shown you a way of doing this, where you'd say that this is really equal to the derivative of u with respect to x. Actually, I take that back. It's equal to, how do you put this again? It's like dy over du times by du over dx, where you take the derivative for y with u. You replace this with the letter u right here. But then you have to chain on the derivative of u with respect to x, and so x squared plus 1 derives to 2x. So hopefully remember doing this, and I'm just going to kind of clean this up a little bit here to help make the point I want to make on the next slide here. Once I'm done deriving this, I can end up getting, well, this 2 will cancel with that 2. Really, there's an x on top, and this negative 1/2 puts this next value on the bottom, leaves you with square root x plus 1. So going from here to here, like I was just saying a few minutes ago, this is a differentiate. This is to take a derivative. Well, what happens if I give you something like this and ask you to do this? Well, this really means to integrate. And this is a lot more challenging, because right off the bat, this isn't something where you can just do what we normally do for integrating. Normally when you integrate, like say x to the n, it's equal to x to the n plus 1 divided by n plus 1. Pop the exponent up by 1, divide by the new exponent. Don't forget to add c. Right? But that's not really going to work in this case here. I can't use that principle. So if I want to integrate, it does help. I mean, this one right here, I know what it's going to be, right? If I went from here to here, it ends up being, well, if I go from here to here, it ends up being a differentiate. So if I go backwards the other way, the antiderivative is what I started with, the x squared plus 1 plus c. So, but I mean, I can't know the answer every single time I go into it. What happens if I'm given something like, and I'm going to skip ahead here, what if I'm giving something like this? Well, I can't just use like an undo a power rule, because there's two things being multiplied by each other. It's almost like I need to have a way of undoing a product rule. So one of the many methods, like I said, we're going to learn by parts, and we're going to learn integration by substitution. That's today's topic. But there are more different tricks you can use to help integrate things that are very challenging. So here's basically the concept. If you were to, now this is really jargon, very, very technical stuff, but if you were to use a chain rule is where you have a function inside another function. The rule is you derive the original function with the baby inside, and then take the derivative of the baby. So we kind of need to reverse that here. We need to find a way to do a reverse chain rule. And basically, this is the really important thing here. In order to do this, what you're going to want to do is you're going to want to take the baby function inside and replace it with the letter u. Just like we did when we were learning how to do chain rule the first time, is replace the baby with the letter u, like this. I'm just going to go back here. This really would have been y equals x squared plus 1. You could have said let x squared plus 1 be equal to u. So then you'd say, well, now I want to do u to the 1/2. But that was with respect to y. This was dy over dx. How do I put this? Now I've replaced this, right? So the way we did that is we said, well, dy over dx can be equal to dy over du times by du over dx. Now, this little bit, I can do the dy over du for this bit here, but I need to do du over dx, which means I'm going to also times it by the derivative, which would be the 2x. So then I derive this guy right here, which is 1/2 u to the minus 1/2, times by the extra 2x on the end here. Replace the u with x squared plus 1. And there we go. That's kind of the basic premise of the substitution. So we have to use that same principle going backwards. So if I get to the example that I've kind of been leaning towards now, first thing I want to do is figure out who I want to work with. So let's let u equal something. Well, where is the baby? Like, who is inside something else? And hopefully you'll agree with me that this x squared minus 5 is kind of the inside something else sort of bit. So what I could do is I could antiderive u to the 8 times by 2x dx. But here's the problem. I can antiderive the 2x dx. That's not hard to do. But u, I can't do that because u is not the right variable. X is the variable. So I need to somehow change this dx into a du. Well, I'm going to do a very similar process than what we did in the regular substitution when you do deriving. I'm going to find the derivative here. And the derivative is actually 2x. Now, one way of approaching this is that once I know this derivative is 2x, I could just say, well, this 2x right here, look, hey, look, I have a 2x right here. I could just plug that right into, well, actually, no, I'm not going to plug that into there. I'm just going to replace these guys here. So it means that I'm going to have u to the 8, but then 2x is actually equal to du over dx. Then I'm still timesing by dx. Well, let's just cancel those then. Now what I've got is the antiderivative of u to the 8 times du. That's awesome. I don't even have x variables anymore. They're all gone. Right? Not only did my 2x go away, but because I substituted it out, but my dx's are gone. Now I'm being asked to antiderive u to the 8 and use my variable. So the answer to this is u to the 9 over 9 plus c. And then I just unsubstitute the u. So u was supposed to be, what was it, x squared plus x squared minus 5. See, there's my antiderivative. I'll call that capital F of x. And if I want to kind of check my work to make sure it's been done properly, think of how this would go. You'd pull the 9 down in front. This would turn into an 8, which is good. We want an 8 there. The 9 that comes in front would cancel this 9 right here, so now both of those are gone. And then you'd have to chain on the derivative of x squared minus 5, which is just the 2x, and hopefully you can kind of see, yeah, that's what we started with. So I'm going to do quite a few examples now just to kind of illustrate how you can use substitution to help you solve. Like I always say, if I lose you or if you have questions, rewatch the little snippet here and ask me. I know a lot of you don't ask me very often, so I hope that means that I'm just doing a really good job of explaining it in the YouTube videos, but make sure you ask when you get lost. So I'm going to do the same thing here. We need to let u, and by the way, u doesn't have to be the only letter you use. You could pick any other letter in the alphabet. It could be A or W. The only letter you probably couldn't use would be X. But I always learn this with the letter u. So I'm going to let u be equal to something. And on this one right here, it actually works really well to make it the 1 minus x to the 3. I'm going to do a little rearranging first, though. I'm going to call this x squared times by 1 minus x to the 3. And I'm going to make that go to the minus 1/2. Hopefully that's clear to you as to why. Now, I'm going to do a couple of substitutions here. The first thing I'm going to do is I'm going to make this x squared, and I'm going to make that u minus 1/2. But I've still got a problem with this dx sitting right here. But I can solve that by deriving this a little bit here. So du over dx, if I derive it, I get negative 3x squared. Now, here's the downside. I don't actually have a negative 3x squared. I have an x squared over here, but not a negative 3x squared. So I found the best way to illustrate this is just to solve for dx, actually. If I were to do some rearranging here, it would look like this. That's how I would get dx by itself. So rather than trying to substitute out the x squared, I'm going to substitute out this dx right here. I'm going to replace it with that stuff right there, which means that I now have du over negative 3x squared. Now this accomplishes two things. The first thing it accomplishes is now my notation indicates that I can derive according to the letter u, which is good. Now it doesn't imply a problem though. I still have x's, but that's the second thing this does. Look, this x squared and this x squared cancel. Now, it really means that there's like a 1/3, negative 1/3 sitting there. So I could really just take that negative 1/3 in front of the antiderivative sign and just do this. I'm just going to derive this stuff here. Well, now this is back to regular polynomials. So this gives you u to the 1/2, divide by 1/2, which is really 2 over 1, add c, and there's my antiderivative. So for my final answer, it's negative 2/3. Then what was u again? 1 minus x to the 3. And that's to the 1/2. There is my antiderivative. And then just to do a quick check, I mean, this is where I'm going to stop. But just to do a quick check, let's consider what a derivative would be. It would give you negative 2 over 3. You then would times by 1/2. You'd keep the baby inside, drop the exponent, and then times by the derivative of the baby. And in doing that, these 2's would cancel, those negative signs would cancel, these 3's would cancel, and yeah, you'd be left with x squared on top of the square root of 1 minus x to the 3, which is what we started with. So I checked my work really fast. So that is one of the nice things about doing antiderivatives, is you should know if you're right. Right? If you've made a mistake, it's either because you couldn't find the trick and you were stumped and you were like, I just can't figure this one out. Or you made a little mental mistake. You made a silly mistake. But you should know if you're right. Well, if you double check your work, it's pretty easy to check pretty quick. So let's try another one, do more examples. Natural logarithm divided by x, antiderive it. Well, same thing here. I can't really use my regular antiderivative rules here. Because, I mean, I can work with x to the minus 1 or 2 or 3, but dividing it by a natural logarithm, we don't have a rule for this one straight up. So substitution sometimes helps. We just have to pick someone to be u. Now, I really have two choices. I either have x or I have ln x. Well, if I just change out u for x, it doesn't really change much. So I think what I should do is I should let u be equal to the ln x, which means when I antiderive it, it's now u in place of ln x divided by x dx. Well, that's no good because I have u's and I'm trying to derive x's, so I need to get rid of that. So the best way of doing this is to take the derivative, and the derivative of ln x is 1 over x. So what I could do is I could rearrange this. I like to isolate for dx. So that would mean I need to take du, I have to times by x, and that would give me dx. And basically that one's going up, that one's going up. So now what I could do is I could write this first bit the same there and take dx and replace it with du times x. Again, two things happen. This u is now matched with the du, indicating that that's the variable we're deriving with. And second thing is our x terms cancel. So all I have to do is antiderive u. Well, that's easy. It's u squared over 2 plus c, don't forget that. Well, since u is the natural logarithm of x, there is my answer. There's my antiderivative. Again, I'll call that capital F of x to indicate it's an antiderivative. Right, and then just do a quick check of your work. Just even do it in your head. The 2 comes down in front, which will then cancel this 2 right here. That'll give you your natural logarithm. And then you'll have to times by the derivative of your natural logarithm, which is 1 over x, which is how the x ends up on the bottom of this fraction. And then don't forget the plus c, because this was an indefinite integral. As soon as we actually want to find the area under the curve, we'll put some values here and here, like an a and a b value. But right here, I'm just looking for you just to be able to derive something a little bit more challenging. So. All right, let's try another one. After a while, you get pretty good at knowing which thing should be your u. It's usually the baby inside. Now, sometimes you have to do a bit of trial and error, and you discover, oh, that isn't the right one. After a while, I start to get pretty quick at these, and I say, okay, well, I'm just going to find what u is, and I'm going to find what dx is, and I'm just going to get those two things just dealt with immediately. So I'm going to take my 2 plus sine x and my dx, and I'm going to do some substitutions real fast here. So I'm going to antiderive, and then the 2 plus sine is now a u. And then the dx is now a du over cos x. And if substitution works, and by the way, I should pause for a second here. Substitution does not work for every single thing. It works really well to undo things that were chain rules. But you need other options as well, which is why you have to do integration by parts as well as other ideas. But if you do this one properly, this one works out beautifully. Well, now to antiderive, you get u to the 11 divided by 11 plus c. And then since u was equal to 2 plus sine x, all goes to the 11, divided by 11. Don't forget to add c because it's an indefinite integral at this point. There we go. There's our antiderivative. And then just in your head real quick, think it through. Throw the 11 down in front. It'll cancel the 11 on the bottom. It'll drop this down to a 10, just like we need it to be. 2 plus sine x will derive to a cos. So you'll have all the pieces you need. You'll have the 2 plus sine still, but now it'll be to the power of 10. And then the cos is sitting afterwards. So the long story short is if you have two things that are being multiplied by each other, as a way to undo a product rule, you may actually have to do this by substitution. Let's try another challenging one here. Sometimes the challenge is to figure out, well, what should the u value be? Right. I'm going to antiderive. Now, I got a couple options. I could try to let the u value be equal to, say, e to the root x. Sometimes you just have to try something and go with it. So if I do that, then it means that my du over dx is going to be equal to e to the root x times by the derivative of the root x, which will be 1/2 x to the minus 1/2. So, I mean, even before I get too much further, that means that it's going to be e to the root x divided by 2 root x. So, I mean, this could work. We'll give it a try. This means that to get dx by itself, dx is going to be equal to 2 root x times by du. I'm going to divide it by e to the root x. So if I do that, let's do some substituting. This e to the root x up there is a u. I still have my root x on the bottom. And I'm now going to times it by dx, which I've, through a long process, determined to be 2 root x times by du. And then I've divided it all by e to the 2x. Sorry, not e to the 2x, e to the root x. Now, a couple of things happen here. First, this guy right here can cancel, and that one right there can cancel. So that's good news, because I no longer want x variables. I also have my du sitting right here. But now the downside is what I'm left with now is 2u du. I could derive that, but sadly there's still an e to the root x still sitting on the bottom there. So that's no good. But wait, hey, isn't e to the root x equal to u? So could I not do a double substitution? And this is where sometimes calculus can be kind of fun, is when you can see that extra step and say, hey, this was u. Watch this. Those guys cancel. I'm now asking you to antiderive 2 with respect to u. This is why right now, I'm so animated right now. This is why this is so important to put this notation here. So important is that now when I'm going to antiderive it, I have to know what letter we're going to antiderive it. This doesn't antiderive to 2x. Incorrect. It doesn't antiderive to 2x, it antiderives to 2u plus c. Because this notation is the one that's sitting here now. And then finally, what was u? Well, u was equal to e to the root x. There we go. There is my antiderivative. And again, if you don't believe me, let's check. Let's try deriving it. So if I try deriving it, it gives me 2e to the root x because it derives to itself. Then we times by the derivative of the root x, which is 1/2 x to the minus a half. This 1/2 will cancel this 1/2 right here. So this will leave you with e to the root x, and then the minus puts it on the bottom as a square root, and ta-da, that's what we started with. So this one was kind of cool. This showed 2 points. First of all, this showed a double substitution. Not only when I did my substitution here did I get to where I got, but I also needed to, at this point right here, when I was still stuck with e to the root x, I could substitute this in a second time, which is kind of cool. The other thing I wanted to point out, this one's so critical. Please make sure you write this notation afterwards, the du. I know in 99 out of 100 cases it's not relevant, but right here it was very relevant. Because if we don't know with what variable we are deriving, it's very different. This is 2u plus c, and then u is the e to the x. But if you had a 2x right here, then it just becomes 2x, and then we're done. And those are very, very different answers. So, okay, so that's it for this lesson here. I mean, it's very straightforward. Once you get the hang of it, I almost always do the exact same 2 things. I find my u, and then I find my du over dx. I rearrange the du over dx to get me dx, and then I plug my u value in somewhere. I plug my dx value in, and if this method will work, then everything should just fall into place nicely. However, not everything will always work, which is why our next topic, when you get a chance to watch it, is integration by parts. And it is another way of being able to differentiate. And I'll even read off the first line here. For every rule that we have differentiation, we're going to need an integration rule. So what we just covered is, well, here's how we deal with a chain rule. If you're undoing a chain rule, do substitution. That should work. But what if you have to undo a product rule? Well, then you can need to do integration by parts. And there's other methods as well, but we're not going to cover those in this course. So anyways, I'll leave that there. As always, make sure you ask me some questions. Please get started on this assignment right away. We are getting close to the end of the year. After this, there's only 2 videos left, and then you've got one last assignment and a final. And it may seem like, oh man, there's nothing left, but I need to warn you, there's still 45% of your grade available. Your midterm's worth 30. All your assignments are worth 30, and your final exam's worth 40. So that means that you've got 40% on this final exam plus a 5% assignment still left, which means that you haven't passed the course yet. Right? Unless you're sitting at 100% going in, you've still got a lot of marks available here. So, which is good too, because if you haven't been doing well, if you work really hard and figure this out in the last little while, you can do well. This is one of the things you'll discover at university is it's high-stake tests. One last thought before I log off. I had a student come back and visit me after his second semester of doing engineering, and he said that he doesn't have any tests that are worth less than, like, say, 50%. He says all of his tests are his big stake tests, like huge final exams worth most of your mark. I think he told me he had one that was worth 70%. You know, his final exam was worth 70, and then all of the assignments and labs before that were worth 30. It was like it really came down to one test. So I'm hoping that by helping prep you for this, that'll give you an idea of what to expect going in next year. But yeah, I mean, I'm not gonna pull punches. Your final exam is worth 40, so make sure that you start prepping for it now. All right, I sincerely hope you're not watching this video late June, but if you are, get to it right away. But I really, really hope that you take my advice and get started on this immediately, so that you're not behind the 8 ball. Because yeah, we're almost done. So okay, anyways, lecture over. I will chat with you guys later.